When you think about the coolest sci-fi creations, like the T-1000 from Terminator 2.
That liquid metal shapeshifter.
Exactly. Or Spider-Man's webbing, something incredibly strong but also super flexible. They all have this combination of softness and immense power.
Right. And for decades, real-world robotics has been, well, the opposite of that. It's been clunky. All metal gears, rigid joints, pistons.
That dream of a machine that moves like a biological muscle has felt pretty far off.
It has. But that's changing.
Welcome to the Deep Dive. Today, we are unpacking a huge leap forward that gets us much, much closer to that sci-fi future. We're talking about an artificial supermuscle.
The research comes from a paper in the journal Science by Xiaoxin Shi, Zhang Zhu, and their colleagues from institutions including Shanghai Jiaotong University.
And their work tackles the core problem holding back soft robotics, something called a dielectric elastomer.
Or DE for short. This is essentially the building block for these new artificial muscles.
Okay, so let's start there. What exactly is a dielectric elastomer? How does it work?
The simplest way to think about it is a sheet of rubbery material sandwiched between two flexible electrodes.
Like a sandwich, basically.
Exactly. And when you apply a voltage, an electrostatic force, it's called Maxwell's stress, squeezes that rubber. It gets thinner, and because it's an elastomer, it expands out sideways.
So you're turning electricity directly into movement.
You've got it.
Yeah.
It's like an electric rubber band.
That sounds almost too simple. If it were that easy, we'd have soft robots everywhere. So what was the big bottleneck?
The problem was a fundamental trade-off. It's like a chemical catch-22.
Okay.
For these muscles to be powerful and efficient, you need two things at once. First, a high relative dielectric constant.
Which means it can hold a lot of electrical charge, right? That's the power.
Yes. But second, you also need an ultra-low Young's modulus.
And that's the measure of softness. It needs to stretch easily.
And there's the catch. Historically, if you made the material better at holding a charge, you made it stiffer.
Ah, so it wouldn't stretch as much.
Right. And if you made it super soft and stretchy, it became electrically weak. It couldn't handle the power, and it wasn't durable.
So you were stuck.
We were stuck. For years, the performance, or the electromechanical sensitivity, was capped at around 110 MPa1. That was the wall.
And this is where the research team comes in with what you called the artificial supermuscle.
They call it the semiseparated biphasic bicontinuous dielectric elastomer, or SBE.
Okay, SBE is much easier. Let's break down that name because it sounds like it holds the secret.
It really does. The core strategy is called hetero-cross-linking induced phase separation.
Which, in plain English,
Means they didn't try to make one perfect material. They designed two different materials to work together inside a single structure, a partnership.
and these are common materials.
Yep, two different commercial silicone elastomers, things like Silgard and Elastosil. This is great news because it means it's scalable. It's not some unobtainium.
So tell me about the two partners in this chemical team up.
Okay, so phase one is what they call the dielectric phase, or D phase. They cross-linked it with high density, which makes it a bit stiffer, but electrically very strong.
That's the power core you mentioned.
That's the power core. Then there's phase two, the mechanical phase, or M phase. This one has low-density cross-linking. It's incredibly soft, with the Young's modulus down around 8 kPa.
The soft skeleton.
Precisely.
Yeah.
The part that allows for massive stretching.
But I'm still stuck on the old problem. If one part is stiff and one part is soft, doesn't the stiff part just limit everything? How do you get around that?
That is the million-dollar question. And the answer is the structure. It's not a simple mix. They created a semi-separated biphasic bicontinuous structure.
Okay, let's use an analogy. It's not a layer cake.
No. And it's not like oil and water. Imagine two different sponges completely intertwined with each other so that both are continuous throughout the entire material.
I see. So they both run everywhere.
Exactly. And the boundaries where these two sponges meet are a little blurry. And this is the aha moment. Those blurred boundaries create what are called dielectric barriers.
So the structure itself adds toughness. It's like having millions of tiny circuit breakers built in.
You nailed it. It massively enhances what's called the breakdown electric field.
It can handle way more voltage without failing.
And that combination, the softness from the M phase, the power from the D phase, and the incredible toughness from the structure, is what completely shatters the old performance limit.
Okay, give us the number. What did this SBE material achieve?
The best version they made, SBE1, hit an electromechanical sensitivity of 360 MPa1.
360.
Yep. More than triple the previous benchmark of 110.
So this isn't an incremental improvement. This is a whole new class of performance. What does that actually mean for a device?
It means efficiency. Massive movement for very little electrical input. It means you can use smaller batteries, get longer run times. It makes the whole concept of a soft robot practical.
And how much movement are we talking about?
Get this, SBE1 achieved 90% area strain. It almost doubles its surface area. And crucially, it does that without needing to be pre-stretched, which was a huge hassle with older materials.
90%. Wow. Okay, so it's sensitive, it's efficient, it's flexible. But does that soft skeleton have any actual muscle? Can it lift anything?
This is maybe the most shocking part. The researchers built a tiny stacked actuator. It was just 4.5 millimeters high and weighed 0.35 grams.
So less than a paperclip.
Way less. A few grains of rice.
Okay.
This tiny actuator repeatedly lifted a 300-gram load.
Wait, 300 grams. That's what? Over 850 times its own weight?
The paper says 250, but your math might be better depending on the exact weight. But then they pushed it even further. At 600 grams, which they state is 500 times its weight, it still achieved a 60% linear strain.
500 times its own weight. That is just, it's like an ant. You know, nature's superlifters, to put that in perspective, that's like a 200-pound person lifting 50 tons.
It's an absolutely game-changing strength-to-weight ratio. And it's not just strong, it's fast.
How fast?
The power density was measured at 2,250 watts per kilogram. And some versions of the muscle hit a strain rate of 400% per second.
So it can move and contract incredibly quickly.
Blisteringly fast.
Okay, so we have strength, speed, sensitivity, but none of that matters if it breaks after a week. What about reliability? Does this complex structure make it fragile?
It's the opposite, actually. The structure makes it far more robust. The fatigue threshold, the point where it starts to break down, was more than 3 times higher than the pure soft material.
3 times is good, but what's the ultimate lifespan?
This is the number that makes it commercially viable. The SBE artificial muscle survived over 100 million actuation cycles.
100 million?
At 260 hertz, so it was working hard.
That's not a lab prototype. That's an industrial-grade component. What would the old material have managed?
The old standard M-phase actuator failed after just about 3 million cycles.
So this is orders of magnitude better. It takes soft robotics from a cool demo to something you can actually deploy for years.
Exactly.
And I read something fascinating in the paper about it being able to sort of manage its own damage, a self-clearing feature.
Yes, this is another really unique layer of reliability. When they coat the SBE with carbon nanotube electrodes, it gains this ability.
How does that work?
Well, over time, any material develops tiny little defects or micropores. Normally, electricity would concentrate there and cause a failure.
The weak link in the chain.
Right. But with this material, when a defect starts to fail, the local electric field essentially burns it out. It creates a tiny non-conductive area around the flaw, isolating it.
So it quarantines the problem spot and the rest of the muscle just keeps on working.
Like a self-patching system. And that's a huge reason to achieve that incredible lifespan.
Amazing. So let's take this wonder material out of the lab. They actually built robots with it, right?
You did. 2 really impressive ones. First was a robotic arm.
Bio-inspired, I imagine.
Absolutely. They used 4 SBE muscles, arranged like biceps and triceps. Because the material is so powerful and can stretch so much, the arm had a huge range of motion, almost 120 degrees.
And it was strong.
It lifted an 80-gram load by over 60 degrees and ran for over 40,000 cycles with no issues. You can immediately see the potential for prosthetics or delicate assembly line work.
And the second robot was even wilder, an ultra-fast crawling robot.
This is where that incredible speed comes into play.
Yeah.
They attached the muscles to a flexible body with little directional feet.
And how fast did it crawl?
It clocked in at a maximum speed of 22 body lengths per second.
22.
Yeah.
That is ridiculously fast for a soft machine. That's biological speed.
And it was incredibly nimble. They could reverse its direction just by changing the electrical signal. And because it's soft, it could squeeze through curved pipes and, get this, they had it navigate a rugged model of a human stomach.
A human stomach. Okay, so the medical applications like endoscopy or internal robots are right there.
Absolutely.
But so many of these cool soft robots are tethered to a wall for power. Did they solve the untethered problem?
They did. And this is the final piece of the puzzle for real-world deployment. Because SBE is so efficient, because it gives you so much bang for your electrical buck.
It doesn't need a giant power supply.
Exactly. They were able to build a completely wireless, untethered, crawling robot They put a small battery and a high-voltage circuit right on its back.
So they cut the cord.
Got the cord. And even though that added a lot of weight, the little SBE actuators were still powerful enough to make it walk and turn. It's a massive breakthrough.
This work by Jiaoshan Shi and the team really feels like a turning point. Let's try to summarize the key takeaways for you.
First, this new material, the SBE, solved the problem that has plagued artificial muscles for decades. That clever intertwined structure finally lets you have maximum electrical power and maximum softness in the same material.
Second, the performance is just off the charts. We're talking a threefold jump in sensitivity, incredible power density, and a lifespan of over 100 million cycles, which is just unheard of. It's robust because of its very design.
And finally, this isn't just a material on a lab bench. It's already powering real-world robots, strong, precise arms, and ultra-fast, untethered crawlers that can navigate places like industrial pipes or even inside the human body.
This research really does move us out of the age of clunky metal robotics and into an era of powerful, flexible machines that start to look and act a lot more like biological life.
So that brings us to our final thought. If this technology lets a tiny actuator lift 500 times its own weight and crawl through your stomach, what is the most complex, delicate task you think this next generation of soft robots will be able to do? Something that right now only a human hand can perform.
A fascinating question to ponder. We want to thank you for joining us on this deep dive. If you enjoy getting the full story behind these world-changing breakthroughs, make sure you subscribe. We'll see you next time.